Okay. Thank you, Costa. It's a great pleasure to be in Athens again for a workshop. So today I want to talk about some work that I've been doing with Maurizio Firota and Ilias Kiritsis. Maurizio is a Marie Curie fellow in Crete. He's an expert in these things, and basically 99% of this work is his expertise. Good. So this talk is about a rather old subject, about highly excited strings. I would like to argue or remind you that excited fundamental strings are interesting systems on their own, even at the classical level. Essentially because they are systems that have a lot of complexity and very high entropy. And therefore, irrespective of whether you, I don't know, like you want to study string theory or whatever, if you're interested in complicated systems, this could be a laboratory where you can study complicated dynamics. For example, if I have an excited string state at some level n, where I excite accordingly all sorts of harmonics of the classical string, then, as you know very well, the mass squared goes linearly with the excitation level. So it goes like n over alpha prime, where alpha prime is the string length squared. And basically, you can count how many modes you can have that have the same mass. And this is a standard computation that you learn the first days you learn about string theory. And you find that at very large n, it goes exponentially as the exponential of square root of n. So you take a logarithm and you compute the entropy, and the entropy goes like square root of n, which you can interpret back in terms of the mass. It goes like the mass, L string times the mass. You can compute the entropy that corresponds to this, and it's just the inverse, sorry, not the entropy, the inverse temperature is just from thermodynamics, the derivative with respect to mass. And you find that it's a fixed entropy, fixed temperature, doesn't depend on the mass. So you have this weird thermodynamics that is called Hagedorn thermodynamics. Good. So basically, the point here is that if you fix n and look at what kind of strings you have, what kind of configurations you have, there can be all sorts of different shapes and sizes with all sorts of with a lot of complexity if n is very large. Now, another reason to be interested in fundamental strings is an old story that goes back to Susskind in '93, which was further debated by several authors, in particular Horwitz and Polczynski, who clarified it a little bit more. And it's the idea that classical strings, as I said, is a highly entropic object. But we know also of other highly entropic objects that we care about, in particular black holes. So on one side, you can think of these two, at first sight, completely irrelevant systems. One that is an excited string. On the other is a Schwarzschild black hole. Let's say we're in 4 dimensions. And then you can ask yourself, is it possible to connect these two objects? So you can try to do it in 2 different ways. You can start from a highly excited string state, make it more and more massive if you want. So at some point it will stop being classical. It will back react in the geometry, and maybe it will become a black hole. Or you can start with a Schwarzschild black hole and start making the Schwarzschild radius smaller and smaller. And at some point you reach the string scale, and maybe there it looks like a string. So you can do a naive calculation. Obviously, going from one place to the other is very hard, because you have to deal with all sorts of dynamical questions. But you can do a naive calculation where you say, okay, I'll take these 2 pictures and I'll try to just linearly extrapolate them from the classical regime for Schwarzschild black holes and from this regime from classical strings. And I'll try to see if anything matches. And you do this calculation. So you set the Schwarzschild radius to be the string scale. And you set the masses to be the same. And that for G Newton, again, in 4 dimensions, that goes like G string squared alpha prime, you find that there is a correspondence point where G string goes like n to the minus 1/4. So this is also an indication of where your classical string description is going to break down. One way to think about it is as I make n larger and larger, it becomes more and more massive. At some point, I will not be able to suppress G-string effects, and the classical picture is going to break down. But then you compute S black hole, so you plug in RH and G Newton in terms of G string and alpha prime, and you find that is precisely square root of n. So the two answers match, they don't have to match, but this is a suggestion that maybe in this interpolation, not a lot of things are varying wildly. And again, you can try to compare this with the situation that we have in ADCFT, where we play a similar game. There we have a D3 brain, for example, or D1, D5 strings. And we go from a weak coupling description to a strong coupling description. At weak coupling, we have the theory, we have n equals 4 super young mills or whatever, the thing that lives on the D brains. And as we increase, basically n equals 4 super young mills G string n, then that description changes, becomes something else, and becomes classical gravity in the appropriate supergravity limit. In that case, so morally it's similar, but in that case we work in an extreme, usually we work in an extremal limit where we can more easily track at least some quantities from one side to the other, and this is how basically DSFT works. In this case, in that case, by the way, since we work in the extremal limit, that's our easiest situation, it's hard to discuss the non-extremal case, which will be the more interesting case if you want to do microstate counting of non-extremal black holes. Okay, in this case, you're starting with a non-extremal limit, so you have finite temperature from get-go, and that makes it more interesting. Now, this story is an old story, and it motivated a lot of work in fundamental, people studying the properties of fundamental strings. There is a paper, for example, from '91 of Mitchell and Suborg that studied the size and shape of excited string states by studying the scattering, 4-point scattering with excited strings. There's another classic paper by Amati and Russo who study emission rates and absorption cross-sections of highly excited string states, and then they also had follow-up work on this. I want to stay with the Amati-Russo paper because, as you can see from the title of my talk, I basically want to compute the same things. So what they did in that paper, it's a nice, rather simple calculation. No, it's Jorge. Yeah. So they computed the average, or the average inclusive emission rate of massless strings from highly excited string states. So basically, you have this process here, where you have a highly excited string state, say at some level n prime, and that string splits up and emits a massless mode with some frequency omega. So it could be a photon, for example, in open string theory, or it could be a graviton in gravity, and leaves behind some new highly excited string state. So you look at this three-point amplitude process. This is a scattering amplitude, you square it, and then you sum over, it's inclusive because you sum over the Hn, the string that is left behind. So you don't really want to track specific processes of what is left behind. You just sum over all of them at a given mass level. So you fix the mass level, but then you sum over all the degenerate states, the microstates that could appear at the end of the process, because you don't want to differentiate between them. Also, another thing that you do is you have this initial state. It could be a very specific microstate of the string at that particular level, but you also average over all of them. So you sum over them and you divide by how many they are. And basically, after you include some appropriate kinematical factors, you can compute the differential emission rate for this process, and that's what they did. So what they found was very supportive for the previous picture of the black hole string correspondence. So they found that when you do this for open strings in D dimensions here, imagine that you have compactified, your extra dimensions that you need to go to 10 or 26 dimensions, depending on whether you do bosonic or superstring theory. Then they found that D gamma goes like this. So you have this Bose-Einstein factor here, which reminds you a lot of black hole physics. If you do it for closed strings, you find this expression, which is again the emission rates that you see in black holes. So that was, like a very characteristic result. And then from these emission rates, they compute gray body factors, or if you want, absorption cross-sections, by using the detailed balance condition, which again is familiar from black hole physics, which assumes some kind of thermodynamic equilibrium. Yes? No. What they did is it's precisely what I mentioned here. So they just did this, and they summed over the states in the light cone gauge formalism. Sorry, that's my fault. So that's what they did. So in a little while, I'll show you our calculation, which is based on the imaginary part of the 4-point amplitude. Yeah. Good. Good. So now what I want to do is revisit basically the same calculation, but I want to do it essentially the opposite way. So instead of first computing the emission rates and then deducing from that the absorption cross-sections, I will first compute the absorption cross-sections by using the optical theorem. So I will start from the 4-point amplitude of heavy, heavy, light, light, or heavy, light, heavy, light. I will cut it in the middle, and this will give me absorption cross-sections. I will take the imaginary part in the forward limit, and so that will allow me to compute exactly the sigmas. Then I will use time reversal symmetries to connect 3-point amplitudes, 3-point scattering amplitudes. 1 goes to 2 or 2 goes to 1. And this will allow me to compute emission rates. There are some differences compared to the previous calculation. First of all, this calculation for the sigmas is exact at 3 level. So in other words, I will not make any average assumptions or a large level limit. So it's exact for whatever string state you have. It doesn't even have to be highly excited, which was a requirement in the Amati-Russo calculation. Along the way, we will find something very surprising, which we didn't know about. And, we'll talk to people, and some people find it natural. Other people say it can't be right. It's very surprising. We'll find that there is a universality property in the absorption cross-sections, which I will explain. And then we compare with Amati-Russo. We find agreement when omega, the frequencies of the light modes, are sufficiently high, when they're much higher than the energy set by the Hagedorn temperature. But for, I will call them superstringy frequencies, but for substringy frequencies, the two results disagree. Okay, so one of the calculations is not right. Yes? No. It's what you want to get the sigmas, and then all the rest is how it should be. Yeah. Good. So let me say a few more words here, like a small parenthesis. This subject, as I was saying, like classical string scattering, obviously takes us back to the 90s. For the older ones, it brings back memories. But there have been a sort of a revival in this subject in recent years. There has been some nice papers along this direction, are papers analyzing the chaotic features of the string S matrix. For example, there was a paper by Gross and Rosenhaus in 2021, and then several papers, some papers by Maurizio, Bianchi, Sonnenschein, Weissman, and other authors that study basically the complexity of string scattering. There have been also other papers where people scatter strings. Strings, again, are massive objects with complicated structure. You would like to see, how you identify this complicated structure in a scattering process and what similarities there are with physical processes, for example, gravitational wave emission. And there has also been a lot of work, mostly by Maurizio, on the efficient computation of scattering amplitudes of highly excited string states using the DDF formalism. So we're going to use two ingredients to do the calculation. One is the DDF formalism that allows us to identify very easily highly excited string states, solves the BRST conditions of quantization of the string automatically. And the other one is the coherent state formalism. Okay, so let me remind you of the first technical ingredient here. So I want to write down the vertex operator of the state that corresponds to a highly excited string state. So this is going to be something very complicated. And solving the conditions for a physical state in string theory in a covariant formalism is, let's say, easy in the first few levels, but then becomes increasingly hard. But if you work in the light-cone formalism, then it's easy. Basically, it's a Fock space of states. So you have, you drop the, you only keep the transverse modes of the string. You use the creation operators and just create states easily. The DDF formalism, but then when you do that, you break Lorentz invariance. But there is a way to do this in a more covariant way, which is the DDF formalism, which basically replaces the creation operators of the transverse modes with this new mode that has a Lorentz covariant index. This is a clever way to build an algebra that is the same algebra that you have with the usual creation and annihilation modes, but at the same time commutes with Virasoro constraints. And Q here is some auxiliary reference null momentum. And then you can create easily states in this formalism in this way. Basically, you just substitute the usual A with this calligraphic A, and you create states in a similar way. Notice that when we do that, there are two kinds of momenta here. We have this momentum, let's say the tachyonic momentum that you have for the ground state. And then A itself also has some null momentum on it. So the physical momentum is what I call Pn, which is P minus NQ. Okay. And in front of it, you have a complicated polarization tensor. It becomes more and more complicated as you go up in level. Again, this thing, just like, for example, P is not the physical momentum, epsilon is also not the physical polarization tensor. We will see in a moment in an example what is the physical polarization. Now, okay, that's good. I was able to identify the states, but I now want to do efficiently computations with highly excited string states. And I need something that allows me to do that. And for that, we use the coherent state formalism. Dimitris Skleros has done a lot of work on this subject. In the coherent formalism, the coherent state formalism, the idea is basically not to solve for a specific highly excited string state, but essentially exponentiate and build one object with some free parameter. It's basically a generating function that you then differentiate with respect to that parameter, and you get the state that you like. So essentially, we have the ground state momentum, and then we exponentiate this Fock space of states with the creation operators, the calligraphic A states. And you see, we dot here with some free parameters that we later take the derivatives with respect to, and we recover the state that we like. This thing can be rewritten conveniently as an exponential of this type in terms of some polynomials, calligraphic S and calligraphic P. The details do not matter. They are explicitly known. And notice that when I do that process, here when I compute this, the lambdas convert into the zetas. Okay, and this is closely connected with how you go from these epsilons to the physical polarization tensors. So the idea now is the following. Suppose that you're interested in the 4-point amplitude. Instead of taking 4 specific states, now you take 4 coherent vertex operators, and you compute that object once. It depends on the lambdas, and then if you're interested in a particular 4-point amplitude, you just take derivatives with respect to the lambdas and get this. Now, that is going to be complicated, but it turns out that it gives you elegant, in some cases at least, it gives you elegant closed form expressions. So let's look at the 4-point amplitude, which is going to be of main interest for us. Here in the open string case and here in the closed string case. If I took the simplest possible case, like 4 tachyons, for example, in the closed string case or the open string case, then you know the result very well. It's the Veneziano amplitude in the open string case. I wrote it here in terms of gamma functions, and the corresponding one in the closed string case is Shapiro-Virasoro amplitude. Now you compute this 4-point amplitude for highly excited string states. It shouldn't look anything like the Virasoro or the Shapiro-Virasoro. Sorry, the Veneziano or Shapiro-Virasoro. But it turns out that when you compute this 4-point amplitude of coherent states, then the Veneziano amplitude or the Shapiro-Virasoro amplitude factorizes out. And it's precisely the factor that contains all the pole structure of the amplitude. So all the rest, all of the other details that have to do with the complicated polarizations are essentially a dressing factor, which is complicated, but it doesn't have to do anything with the pole structure of your amplitude. And then again, all these Ks here and all the phis here are known explicitly. So let me give an example so that it's not very abstract. So let me consider, for simplicity here, the 4-point amplitude of a highly excited or an excited string state with a tachyon. The excited string state looks like this. There is a polarization tensor here. You see I have G1 modes of A-1, G2 modes of A-2, etc. And there is some polarization tensor here. This is the state. So what's the idea here? I take the generating functional with 2 coherent vertex operators, 2 tachyons. There are 2 types of lambdas, lambda 1 and lambda 4, for the 2 excited string states. And then I take the appropriate derivatives with respect to these lambdas and contract them with the epsilon that I like, epsilon 1 and epsilon 2. Okay, so that's the general idea. And for leading edge trajectories, wait, what happened here? Something disappeared here. Okay, that's very interesting. Okay. Okay. So what I was going to show here is the case where I take a leading edge state so that it's simple. You see here I activate only A-1, contract with a polarization tensor. And for even more simplicity, just for illustration purposes, I was taking the case where the epsilon mu1, mu2, etc. is just has a factorized form. So it's basically lambda 1, mu1, lambda mu1, lambda mu2, lambda mu3, etc. So just the product of a single vector lambda. And then what you will find here, hopefully in the slides that are posted, you see a very explicit closed form expression for this generic level state, written very explicitly down in terms of contractions of the polarization tensors with the momenta. Okay. Now, let's go back to our purpose, to our goal. Our goal is to compute absorption cross-sections. That's the first thing we want to do. So, again, I want you to focus here. So I have state 1, state 2. State 1, think of it like this. State 1 absorbs state 2, and then it produces something. Obviously, this can happen in many different ways, right? Like I produce 1 state, or I produce 2 states, 3 states, 4 states. But 2 states, 3 states, etc. are down by powers of G string. So at leading order in G string that I'd like to work, I can only, it's enough to consider only processes where I have state 1, absorbs state 2, goes to another state 3. Okay? So I compute the 3-point amplitude, which is in the similar spirit as Amati-Russo. I take this 3-point amplitude, I square it, I sum over all the states in n prime, all the microstates at the fixed level n prime, and that gives me the inclusive absorption cross-section that I care about. Now, how am I going to get this? Since I know how to compute efficiently 4-point amplitudes, I take the 4-point amplitude and I apply the optical theorem to that. So basically, I take the forward limit, I identify the pole, take the imaginary part, and that basically it's a Katowski rule. It allows me to cut the propagator there and get information about the complicated thing that, otherwise I will have to do it term by term, and it's very complicated. Okay, so now I have an expression for the 4-point amplitude. It may be complicated. In general, it is very complicated. I have to take a limit on that, and I compute. Okay, so this is precisely what is written here. This sigma that I care about is related to the imaginary part in the forward limit of a 4-point amplitude, which is essentially this quantity with some kinematical factors in front. And then basically identify the pole and compute. So, when I do this computation, I start with a generic, this doesn't have to be heavy light or whatever, just like take 2 generic excited string states going to 2 excited string states. This is going to be, in general, a very complicated result, right? Because you have this excited string states, they have this complicated polarization structure. In general, the result is going to depend in a very complicated way on the polarization structures, okay? But then a miracle happened, which we didn't expect. You do the computation, and the result doesn't depend at all. In the forward limit, it doesn't depend at all on the polarization structures. It only depends on the levels. Okay, so all that complicated structure in that limit went away. Okay, and this is what we call the universality property of the scattering cross sections. So this is just forward limit, 0 transfer momentum, yeah, and you take the imaginary part. Yeah. Which one? Sorry. Here? No. Yeah. Well, it doesn't have to be, no, here I'm just doing a generic computation, right? It doesn't, that's why I'm saying that this is exact compared to the Amati-Russo. I don't have to take any heavy limits. It's just like generic states. They could be light, they could be whatever you like. Okay? So it's generic computation. At this point, I haven't taken any large level limit. Okay, so and indeed we saw a lot of examples, several examples in the paper where we do low-level calculations explicitly without using the formula to see if we get the right result, and it agrees with our general result. So that means, for example, that if I average, for example, over the initial states, 1 and 2, okay, it doesn't make any difference because the result, again, averaging over the microstates at specific levels doesn't make any difference because the result is always the same for all the microstates. Okay. Okay, so now let me show you what you get, for example, for the absorption cross sections when you have a light mode. And let's say we go to the frame of the heavy particle. Okay. Then for open strings, I get an absorption cross section that is frequency independent. Okay. For closed strings, I get an absorption cross section that goes linearly in the frequency. Let me remind you for black holes, when I take the 0 frequency limit, sigma goes to a constant, and that constant is proportional to the area of the black hole. Okay, so in other words, essentially when you do scattering, the size of the target that you look like represented by the scattering cross-section is basically the size of the black hole, the area of the black hole. Okay. Good. And by the way, already here, if you compared with Amati and Russo, you will see that there's a difference. Because there's already, you can see here, when I take omega goes to 0, it's not the black hole result. In other words, there is a non-trivial gray body factor for excited strings, and when omega goes to 0, it's like they have 0 size. Okay. So now let me go to the second part. Now I want to do the opposite. So now I want to compute emission rates. Okay, so how do I do that? Now for emission, you take an excited string state and you want to split it into two. So you have state 1 goes to state 2 and 3. Okay. So you compute the differential cross-section with respect to the energies of one of the produced states. There are some kinematical factors. It's not important. We have the conservation of energy. And then the whole result is proportional to the 3-point amplitude squared of state 1 going to state 2 plus state 3. Okay? And now our idea was not to use any assumptions about thermodynamic equilibrium, or if you want the detailed balance condition. Our idea was to simply use the time reversal symmetry and relate this amplitude with this 3-point amplitude with a complex conjugate of state 2 and 3 going to state 1. Okay. So remember in the previous, so this was involved in the previous calculation. I had two states, or one state absorbing another state, goes to a third state. And then because I was using the optical theorem, I was naturally summing, it was inclusive, so I was summing over the states. Okay, so I want to do the same thing here. So, I compute now, or if you want, I define a new differential cross-section, which again is very similar to what Amati and Russo. It's the same thing that Amati and Russo computed, where I take that, I take that previous differential cross-section and I sum over the initial, I average over the initial states. Averaging over the initial states is essentially doing the sum that I was doing before in absorption. But I also sum over the final states, okay? Because I want it to be inclusive now as an emission cross-section. Okay, so, and here comes the key point. I take this equation here, and basically I do three sums. Sum over the initial state and the two final states. That's all I do here. And I take an average with respect to the density of states in its sector, for its state, at its level. Okay, so this is A equals A dagger. I just squared things and I summed. That's all I did. But now notice on the left-hand side, this is essentially absorption, right? So, and there I had noticed I have computed this thing, and I know that it doesn't depend on the details L1 and L2. It doesn't depend on the details on the microstates of the initial states. So I can basically remove these two sums and the two rows because they don't play any role because of universality. And that's precisely what gives me the right hand, this equation here. I removed the sums over L1 and L2. Here I keep the three sums, here they are. And then I took these two density of states, I brought them on the numerator on the other side, here they are. Okay, so now I have this left-hand side is equal to this right-hand side. This is precisely sigma absorption that I computed before. And this is now essentially what Amati and Russo were computing. Okay? So in this way, but the universality was very important in order to do this, to be able to do this step. In this way, I can connect my computation for absorption with emission. And now let me show you results. So let me consider the case where I have, let's say, an excited string state. It emits a photon in open string theory. Again, I don't need to take n prime to be very large here, which was part of the assumptions in the Amati-Russo calculation. You get a more exact formula, if you want, that looks like this. The interesting limit here is the limit where the state is highly excited. So I take n to be very, very large, n prime to be very, very large. And also now I have to think about where the frequency of the emitted photon is compared to that. Okay, it could be very, very large and can be computed from this one. But the case that also Amati and Russo very rightly are considering is the case where this is much smaller than the mass of the emitted state. Okay, so in this limit, That rho gets approximated by exponentials, and you get a Boltzmann factor, a dropping exponential, hinting at the thermodynamics of the highly excited string state with temperature set by the string scale. Now, if I go back to this result, this is the result I should be comparing with, it's exactly the same, when you consider exactly the prefactors, all the prefactors match, but, and when you take omega much larger than Th, basically you can drop -1 and you get the exponential. All the right, you get the right omega factors, etc. Okay, so the two results agree, but they agree in a limit where omega is super stringy, right? It is much higher than the Hagedorn temperature. Good. And again, the same, and it deviates numerically, not by a lot, by the way, but it deviates when omega goes to 0 from the previous result. Yes. Question. Yes. I think. Yeah. I think. Yeah. I think. Yeah, I have to check if we did it numerically or whatever, but we could check. We could make numerical plots. Okay, now you do the same calculation for the closed string, and it's very similar. Basically, things square. And you go again in the same limit, and you get a result again, not with the full Bose-Einstein factor, but with simply the exponential, which again agrees with all the prefactors and all the omega dependence with the result for Famati and Russo, but not at very low frequencies. And so I'm doing good on that, right? Okay, good. So that's basically the result I wanted to report. It's a little bit surprising, especially this universality property, but it turns out that in the forward limit, things can simplify a lot. We verified again that highly excited string states exhibit a thermal emission spectrum, but now they have non-trivial gray body factors. This is a new result. Also, the universality property is a new result. I have to emphasize here that these computations are possible because of powerful tools provided by the DDF formalism and the coherent state formalisms. And now that we understand them a little bit better compared to the past, I think there is an opportunity to do all sorts of new calculations in this area. Already tree-level is certainly possible, and then there are also some one-loop calculation, higher loop calculations that you might be able to do. And then there are all sorts of physical questions, like gravitational wave of emission or whatever, that you can revisit in this context, and some of these things we are considering at the moment. So let me stop here. Thank you.